So we know that the change in energy of an object is equal to the external work I do on it, which is the dot product of force dot dx. And probably rather than dx, I don't want to get x confused with y. I don't want displacement to be confused with x and y. I should say the vector dot product of force and displacement. What I mean is, we already knew that if I pull up on a box, I don't do any work if it's moving in this direction. But if I push it in this direction, because there's some displacement in this direction, then the work is the force I put on it times that displacement. And that work would go to a change of kinetic energy or heat if there's friction. But what if I pull at an angle, let's say like this, with let's say 100 newtons? And now what we want to do is recognize that this force vector could be decomposed into a horizontal force that does work because we're moving in the horizontal direction, and a vertical component that doesn't do work. And this would be, let's say, about 70 newtons, and let's say about 70 newtons because 100 newtons is, we can see that this is a little bit larger than that. And then I could say, if V naught is equal to 0, then the initial kinetic energy is equal to 0. And then the work I do on it is equal to the final kinetic energy, is equal to 1/2 mv squared final. So let's say I pull at this angle with 100 newtons for 2 meters in the x direction. Now I can say, oh yeah, the work is the vector dot product of this displacement and the force. And so that's just this component, which would be the 70 newtons times the 2 meters. That's going to be equal to 140 newton meters, or 140 joules. Now let's say I wanted to know what the speed was. I could go in a force and kinematics route, but I could also say, look, the work I do is transferred to kinetic energy, and then I can just solve this for the final velocity. And substituting in, we have 2 times 140, and I'm going to write joules as kilogram meters squared per second squared, because I know I'm going to cancel units, and this is a 10 kilogram box. And so I cancel my kilograms, and this cancels 1, and I end up with 28 meters squared per second. This is a wrong unit, so I forgot to put down this. I have to take the square root of this, so then I have meters per second. And the square root of 28, I don't know, the square root of 25 is 5, the square root of 36 is 6, so this is 5 plus meters per second, maybe around 5.5. How different this might be if I was pulling at a very high angle with this 100 newtons. Now what would it look like? Well, at a very small, like maybe this is on the order of 15 degrees, but I can just look at this and see if that's 100 newtons, this is on the order of 20 newtons, 1/5 that length. And the work, or the change of kinetic energy, which is the vector dot product of force times displacement, would be equal to that same 2 meters, but now only the horizontal component is just 20 newtons, giving me 40 joules. And so the final velocity, which would be 2 times that 40 kilogram meters squared per second squared divided by the 10 kg, would be just equal to the square root of 8, almost the square root of 9, so slightly less than 3 meters per second. So what if we were pulling up an inclined plane, this same box, at that same angle? Now we see it would be different because this is my 2 meters of displacement. So in order to find the work here, we wouldn't be looking at the horizontal component of this force. We would be looking at the component of the force parallel to our direction. So in this scenario, my tension would be doing more work than it would be in this scenario, because the displacement is more in the same direction as my force.